Alright guys, let's look at this counting problem. This is an interesting one. In some sense, it's a two-step counting problem. So we want to know how many non-negative integers, so non-negative, so we're not going to include negatives, but we are going to include 0. We want non-negative integers less than 1 billion that have exactly 5 sevens. So 1 billion, if you remember, looks like this. So any number less than it is going to have, at most, 9 digits. So we can look at it like this. And we can even think of the number 112 in this form, because we'll just have 112 like this, 112, and zeros in the other spots. So we'll think of this as the number 112. So we want to know how many non-negative integers that look like this have exactly 5 sevens in them. So, well, let's think about it. Let's think about one arrangement. 3, 4, 5, 6, 7, 8, 9. So we had 9 spaces. And one arrangement, well, let's have all our 5 sevens at the beginning. So we have our 7, we have our 7, we have our 7, 7, and 7. So I'll use red to say that's the actual number, and the color white will be how many choices we have for the other ones. So we know we have exactly 5 sevens, so how many choices do we have for this digit here? Well, there's 10 digits, 0 through 9, but we can't pick 7 because then we'd have 6 sevens. So there's only 9 choices left for us here. 0, 1, 2, 3, 4, 5, 6, 8, and 9. And again, there's 9 choices for that digit, our second last digit, and our last digit. So if we have 5 sevens at the beginning, we have 9 choices for each of these digits, and our first 5 digits are chosen for us, so we don't have any choice there, or we could say we have one choice, a 7. So with all 5 sevens at the start, we have 1 times 1 times 1 times 1 times 1 times 9 times 9 times 9 times 9, which is 9 to the 4th. And you can work that out, that's 6,561 different numbers that have the 5 sevens as the first 5 digits of your number. And you can imagine there's nothing special about having the 5 sevens at the start. The same argument would hold with the sevens other places. So let's see another arrangement. So let's have the sevens in the second, the 5th, the 8th, and the 9th position. Oh, we need one more. Let's have it in the 4th position as well. And again, those are chosen for us. And we have 9 choices for all the other digits. So it's going to be the same thing. So we know this is going to be 6,561 numbers that look like this, where you have sevens in the ones digit, tens digit, the 10,000s digit, the 100,000th digit, and the 10 millions digit. So now the question becomes, now that we know this, the question becomes, well, how many different ways can we arrange our 5 sevens among 9 digits? So that's our new question. How many ways can we arrange our 5 sevens in 9 digits? Once we know that, for each of these arrangements, we know we're going to get 6,561 numbers. Well, this becomes an arrangement problem. We know how to deal with those. Well, we have our 9 digits, so we need to arrange them. And there's 9 factorial ways of arranging 9 digits, but we have 2 groups. We have the groups that are the 7s, we know we have 5 of those, and we have the other digits. And all we care about is where the 7s are and where the other digits are. So the order of the 7s and the other digits doesn't matter. So just to count how many there are. So we know we have 5 7s and 4 other digits. Our set kind of looks like this, right? We have 5 7s and 4 blanks. And this, we don't care about the order of the 7s, they're all the same. We don't care about the order of the blanks, they're all the same. So the number of ways we can arrange 5 7s and 9 digits, well, let me erase that or scratch that out, that's just getting in the way. It's going to be how many things we have, 9 factorial, and we're going to divide by the size of each group where order doesn't matter, factorial. And if we do that calculation, well, we're going to guess, well, let's do 9 factorial divided by 5 factorial. So that's going to give us, we'll cross that out, so 9 times 8 times 7 times 6. So the 5, 4, 3, 2, and 1 are all canceled out in the 9 factorial because of this 5 factorial. And we're going to divide by 4 times 3 times 2 times 1. And let's cancel it a little more. So, well, we can divide the 3 and the 2 here into the 6. So that's gone. And then we can divide the 4 into the 8 so that this becomes a 2. And so we're left with 9 times 2 times 7. I know 9 7s are 63, so 9 times 2 times 7 is going to be 63 times 2, which is 126. So I know that there are 126 ways of arranging my 7s in the digits. And for each arrangement, I know I have, so that's the first fact. The second fact is for each arrangement, I have 6,561 numbers. So, the total number is going to be, well, I have 6,561 different numbers for each arrangement, and I have 126 arrangements. Well, if I calculate that, I guess 826,686. So, out of all my numbers, my just less than 1 billion numbers, 826,686 of them will contain exactly 5 7s.